Hey guys, welcome to the physics-based tutorials. Today we're going to focus on solving a problem where we have a pulley that has mass in this Atwood machine setup. So you're going to learn how to draw force diagrams for the pulley itself and also the hanging masses. We're going to write some net force and net torque equations for the pulley and masses and use systems of equations to calculate the linear acceleration of the masses, and the angular acceleration of the pulley. So this video is really going to help you out if you're in the rotational motion unit of a course like AP Physics 1 or AP Physics C Mechanics, or if you're just taking any other physics course and you're in the rotational motion section. So our problem here today, we have an Atwood machine that consists of a 0.3 kilogram pulley with a radius of 0.24 meters. We have two blocks attached by a string. We have the masses of those blocks. We know they're released from rest. We're going to calculate the acceleration of the blocks and the angular acceleration of the pulley. Okay, so to start, it's always a great idea to draw yourself a little sketch of the situation here and give each mass a label like M1 and M2. So here, we'll draw our pulley. On the left, we'll draw in there mass 1. And over here, we'll draw mass 2. We're going to make sure that we label those so we know which is which and which directions that they're accelerating in. So we'll make mass 1 will be our heavier mass. Our mass 2 will be our lighter mass. And we'll also write in here the mass of our pulley at 0.3 kilograms, and we're also given the pulley radius. Okay, so given that mass 1 is the heavier mass, we want to think about the direction of acceleration for all of these things, mass 1, mass 2, and the pulley. So mass 1 is going to accelerate downward. Mass 2 is going to accelerate upward. And then the pulley is going to have this angular acceleration in the counterclockwise direction. So one thing to note about this kind of system, the pulleys or the masses have the same acceleration. So the acceleration here of mass 1 downward is the same in terms of magnitude of the acceleration of M2 upward. And this angular acceleration is related to those accelerations by this equation. So our angular acceleration would be the linear acceleration of the masses divided by r, the radius of the pulley. Okay, so we're going to use that in our equations here. The next thing that we're going to do, though, is we're going to draw three force diagrams. One for the pulley, one for mass 1, one for mass 2, and that's what's really going to help us write a net torque equation for the pulley and net force equations for the two masses. So for our pulley, we're pretty much going to worry about the two important forces here. It would have a supporting force, it would have a gravitational force, but those two forces would be acting at the center of mass, so they're not exerting any torque. We're not really concerned about those. On the left-hand side of the pulley, we have this downward force. We'll call this T1 because this is related to mass 1. And we also then on the other side have T2, so tension forces from the strings. So those two tension forces are different from one another. If they were the same, our pulley would not undergo any angular acceleration. It would either stay at rest or it could be just moving with a constant angular speed. But it does have angular acceleration here, so those two tension forces are not equal to each other. This is a little bit different than back in the day when you were talking about like just plain old Newton's laws and you had an Atwood machine, but the pulley wasn't rotating. The string was just like sliding over the top of the pulley. But now that we have a pulley that is moving, it has angular acceleration and rotational motion. These tension forces are not the same and we can't treat them as if they are the same. So we have to make this force diagram for our pulley. For mass 1, now mass 1 is accelerating downward. It has a gravitational force acting on it equal to m1 times g. And in the other direction, it has this force T1. Okay, so T1 here and T1 here, those are the same. They're the same tension force, just coming from like kind of opposite sides of the left side of the string. But that gravitational force is larger than the tension force because M1 is accelerating downward. M2 is accelerating upward. So it has upward this tension force T2. And that is greater than the gravitational force acting downward on it, which is M2 times G. So again, also here, this tension 2, T2 over here, is the same as this tension force over here in terms of magnitude. So what are we going to do with these force diagrams? We are going to use them to now write a net torque equation for the pulley and net force equations for our two masses. What you're going to see is that we have three unknowns, which are going to be tension 1, tension 2, and acceleration. And we're going to create these three equations to do the process of systems of equations. So for our pulley, we're going to work off this idea coming from the rotational version of Newton's second law, which is that net torque is equal to the moment of inertia times angular acceleration. And the moment of inertia, or the rotational inertia of a pulley, we'll assume it's a solid disk, is equal to 1/2 its mass times its radius squared. And then also too, we're going to use this relationship that I mentioned before, that the angular acceleration is equal to the linear acceleration divided by the radius. We'll see how that plays into this in a second. But to write a net torque equation for the pulley, the net torque we'll write also for torque is equal to force. This is just to calculate an individual torque, is equal to force times radius times the sine of the angle between the force and the lever arm. So for our pulley, we have the torque exerted by force tension 1 and the torque exerted by tension 2. And like I mentioned before, they're working in opposite directions. So we're going to subtract these. So T1 times R will leave off the sine theta because it's 90 degrees. So if we're talking about the lever arm, that would be right here. That's a 90-degree angle. The sine of 90 is 1, so we don't really need to worry about that. Minus T2R, so there's an expression for the net torque, is equal to 1/2 mr squared. And I could write in the angular acceleration here, but just to save a step, rather than writing this, we'll swap in already this linear acceleration divided by r. And so notice something here, all of these r's cancel, so we can like cancel one of these with that one, and then we have an r in each term. So our r's, we get rid of all of those. That cleans this up a little bit, so we have T1 minus T2 is equal to 1/2 m times A. So that's what our net torque equation for the pulley kind of boils down to. So let's kind of repeat that process with our masses, but for net force and like the regular version of Newton's second law for both of these. So for mass 1, we have the gravitational force M1G minus our tension force T1 would be equal to M1 times A. And then for our other mass, tension 2 minus M2G is equal to M2 times A. So again, here we're working off of Newton's second law, where net force is equal to M times A. So the reason that, if you're curious about like, why are we writing the forces with these particular signs? So setting them up this way and like subtracting them in this particular way is important. So we can almost think of this in terms of like helping minus hindering in terms of how these forces are interacting with like the masses and the directions that they're moving in. So the M1G, the gravitational force on M1, this is kind of like quote unquote helping in terms of the direction of acceleration of the pulley. This one is hindering. So that's why when we look in these equations, this term M1 times G is positive, but M2G is negative. So again, if you take a quick look here, we have our three unknowns, so T1, T2, and acceleration. And we have three equations. We have our equation from the pulley, we have our equation from mass 1, and we have our equation from mass 2. So essentially what we're going to do here is we're going to rewrite our equations for the masses. We're going to solve them for the tension forces and do a little substitution into our pulley equation. And we're going to be able then to solve that equation for A. So let's take a look at how that's going to kind of work out here. So to start, our force tension 1 is equal to M1G minus M1A. Our force tension 2 is M2A plus M2G. Okay, so let's take our equation for the pulley. We're going to do a little substitution here. For M1G minus M1A, there's our force tension, our expression for tension 1. And we're going to subtract M2A plus M2G and set that equal to 1/2 M times A. All right, so we're going to take this equation, we're going to get it set up to solve for A because we have our masses. Just quick note here, this mass right here is the mass of the pulley, and we have mass 1, mass 2. We know what G is, of course. We'll use 9.8 meters per second squared, or 10 if you like, but we're going to go ahead and solve for A. Okay, so now we have our expression for the acceleration. Again, this acceleration here that we're talking about, you'll notice when we plug this in, we're getting a number that has the unit meters per second squared. That is the linear acceleration of the blocks, which is also the linear acceleration of the pulley too. But then we'll have to do one more step to get the angular acceleration of the pulley. So let's go ahead and plug in our numbers. We'll see what we get. All right, and so 1.8 meters per second squared is our answer here for the linear acceleration. And for our angular acceleration, we'll take that linear acceleration and divide by the pulley's radius. So 1.8 meters per second squared divided by 0.24 meters gives us about 7.5 radians per second squared. So 1.8 meters per second squared, 7.5 radians per second squared. All right, so just to recap what we did there, some important points of our process. If you're looking to kind of think in terms of a problem-solving strategy here, anytime you have a situation involving forces or torque, it's always a good idea to start off with a sketch and then a force diagram. So we first drew a force diagram for each one of our objects. We wrote net force equations for our two objects that were moving with translational motion only. And we wrote a net torque equation for our object that was undergoing rotational motion. From our net torque and net force equations, we were able to get them all in the same terms, so getting our accelerations both in the form of the linear acceleration, and we substituted to get those tension forces out of there because we don't know what they are. And we got our equation in a form where we have only one unknown that we were able to solve for that linear acceleration. And then finally we used our conversion from linear quantity to an angular quantity to solve for our angular acceleration of the pulley in radians per second. So hopefully that was helpful to you. I know pulleys can be a little bit tough, especially when we're now taking into account the rotational motion of a pulley, but it's, if you make the diagrams, it becomes pretty simple to now write these equations and just do a little bit of substitution. So if you're looking for more tutorials like this one, I'll link a few. If you're in this rotational motion unit, there's a lot of different things that we can take a look into. And if you want more resources, more videos like this, we have some online courses coming out soon and some other free resources, especially for studying for the AP Physics exams. Head on over to thephysicspace.com and take a look around. We have new resources coming out all the time. And if you sign up for our newsletter, you can get notifications for whatever course you're actually taking, so you know when we're coming out with some new stuff. All right, I hope to see you next time.